All right. So we have a few topics left. We have this one. We have graphs and functions and relations. So I think that's the last. I think that's it. Those three topics. So I am, just so you know, there are links to these posted in our Fast Track lessons videos repo, if you're looking for them. And I've got all the slides up here. Oh, Matrix. I forgot Matrix. Can't forget Matrix. That one's so much fun. Well, it's not the same. And I even have a slide that says that. So that's what we're going to do next week. We might have to, so you have to do this maths test before the end of term 2, which means it's possible we might have to double up 1 week to get all the content done before you need to take a test on it. So I'll have a look at the calendar and work that out. We might do graphs and functions and relations in the same week. Those aren't too terrible. Matrix can be a little bit overwhelming for people because it's really mathsy. It's very mathsy. So there's calculations and stuff to be done in the matrix unit. There's a little bit of that in this one, in Big O notation. You'll see some maths terminology in this one, like logarithm. You don't have to do any logarithms, but the term is there. Yeah, so this is what we have left. And there are the slides. So I will stick the link to this one in Slack really quickly, so you can pop that up and follow along there if you like. So did you see Karen threw out a challenge in Code Wars? I just posted that in the Slack channel. Who does Code Wars? Are you in the Coder Academy clan? So if you join the Coder Academy clan in Code Wars, then you can compete with Kieran. He's at the top and he's bragging, and so I'm sure that someone can surpass him. Okay, so in lessons, I'll stick these links. This link to the Maths Big O notation slides. Okay. So what is Big O notation? It's used in computer science and other fields, but in computer science it's used to indicate the performance or complexity of an algorithm. And the couple of important things to know about this. One is that it tells you in a worst case scenario what the performance or complexity is. So it's not in the average case or the best case, but in the worst case what the performance or complexity is. And what it really is a measure of the rate of growth of the performance or complexity with respect to the input data. So as the input data size gets bigger, how quickly does the complexity grow, or the amount of the execution time, or the amount of memory taken? Several things could be measured by this. A lot of times in computer science we think of it as execution steps, how many steps we have to take in order to execute the algorithm on the data set. And then we look at how fast does the number of execution steps grow with the size of the input growing. Okay, so it's a rate of change measurement. So here's a graph. And what this graph shows you, what it demonstrates, is with different orders of complexity, the way that they increase with an increase in the size of the data set. So across the horizontal axis, from left to right, we have a growing data set size. Okay, so as we go further to the right on this graph, the data size gets bigger. So maybe we have, an array of some number of values, and that number of values in the array is growing as we move to the right side of that graph. And then on the vertical axis, we're measuring the number of operations or execution steps that are performed as that data size grows. So you can see that the sort of, what do I want to call it? I don't want to use the word order, but I'm going to use the word order. So the order that that these different big O notations are in relation to that. So the best performing is one way to think of it, is a constant order. So big O of 1 where it refers to a constant order of complexity, and I'll talk about what these are in a minute. And at the very top, the top line with the really sharp curve is the exponential order of complexity. So that's the worst performing. Okay. So first of all, let's make sure everybody remembers what an algorithm is. I'm sure you do. An algorithm is just a set of steps used to solve a problem for any given input. That's all that it is, a set of steps to solve a problem. So some examples are a searching algorithm is a set of steps that are executed to find a value in a list of values. A counting algorithm is a set of steps to count the instances of one thing in a group of things. A sorting algorithm is a set of steps to put a list of things in a specified order, like smallest to largest. Those are all examples of algorithms. So here are some common big O notation names, because you'll see on the left is the notation that you'll see related to these, and on the right is the name that you might see them referred to. And these are listed in order of complexity from least complex to most complex. Okay, so the least complex is a constant order of complexity. After that comes logarithmic. We're going to talk about these in more detail. Then linear, then quadratic or polynomial, and then exponential. So we're going to talk about each one of these, what they mean, and I'll give you examples of each of them. Okay, so part of this is understanding, sort of getting a sense of what these orders of complexity are. And then the other part of this is being able to look at an algorithm and recognize or sort out, work out what is the order of complexity of that algorithm. Okay, so the constant order of complexity. If an algorithm always takes the same number of steps regardless of the input size, doesn't matter how much the input size grows, we execute the exact same number of steps every time, then it's said to be constant. So one example is a function that returns the first element of an array. It doesn't matter how big the array is. It can have 1,000,000 items or one item. We're going to execute the same number of steps for that algorithm. Does that make sense? So that's the simplest one. Next is logarithmic in the order. Okay, so logarithmic sounds scary because it has the word logarithmic in it, but it isn't too bad. So logarithmic is when we can discard. Typically, we're talking about log base 2. Okay, so it typically means when we can discard half of our list with each execution step. Okay, so every time we look at this list, we can cut off half of it before we look at it the next time. And so we have the list with each execution step or each time through the loop. So an example of this is binary search or merge sort. Those are both examples of a logarithmic order of complexity. And what happens is each time through the loop, we either just look at the bottom half of the data and throw away the top half, or we look at the top half of the data and throw away the bottom half. So each execution of the loop, we cut the list in half, and that's why this is logarithmic complexity. So let's look at an example in more detail. Let's look at binary search. In binary search, we have a sorted list already. Okay, so we already have a list that's sorted, and we're looking for a value. So at the start of this algorithm, we determine the midpoint, which is just the middle index. Okay, so that's a simple calculation, length divided by 2, basically, right? And we look at that one. And then we say, okay, is the value we're looking for equal to this value? If it is, we're done. Is it less than this value? And if it's less than this value, we throw away the top half of the list. And if it's greater than this midpoint value, then we throw away the bottom half of the list. And then we execute the loop again. And at the top of the loop, we find the midpoint, and we do the same operation. Okay, does that make sense? So you can see each time we go through the loop, we're going to cut the list in half. So in a worst case scenario, it's going to take logarithm base 2 steps. Logarithm of base 2 of n steps to do this algorithm. So don't worry about what that is. You just know that you cut the list in half every time. Okay? Now this is the second fastest order of complexity. It's faster than linear. Does it make sense that it's faster than linear? So linear is we do one execution of the loop for every element in the list. So as many elements in the list we have, that's how many times through the loop we have to go. So you can see how this would be faster than that, right? Because we're cutting the length of our list in half each time we go through the loop. So that's going to be faster. Okay? Linear algorithm requires as many steps as there are values in the input data set in the worst case. So an example of this is a function that counts the occurrence of an element in a list. So say we have a list where an element can be duplicated, and we want to count how many times that element occurs in the list. Well, we would have to look at every single element of the list, wouldn't we, for this one that we're searching for, and we would count the occurrences of that element. So if we have a list of 10 things, we're going to have to look at 10 elements. And if we have a list of 1,000,000 things, we're going to have to look at 1,000,000 elements. So the complexity of the algorithm, the number of steps we have to take, grows exactly with the number of inputs that we have. So that's why we call it a linear complexity. Does that make sense? A lot of our algorithms are linear. A lot of our algorithms are linear. And the ones that aren't linear are quadratic or polynomial. So quadratic or polynomial is what we see in nested loops. Okay? So these execute some set of actions over the data set up to n times for an n-size data set. So an example of this is a basic sort, like a bubble sort. And so in this kind of sort, we have an unsorted list of elements, and we get them into order by comparing each element to the one next to it. And if the one next to it is, say we're sorting from smallest to biggest, if the one next to this element is smaller than this element, then we swap them. And we go through the list, and we do that for every element. And then if we didn't sort everything, we go back through the list and we do it again. Okay? So potentially, we could have to do that. Say we have a list of 5 things. If they're in reverse order, then we're going to have to do that switch all the way through. That's going through 5 times, and we'll have to do that switching loop 5 times to get the whole list sorted. So that's 5 times 5. Okay? So a lot of algorithms, most of the algorithms that we see and use are either linear or they're quadratic. And so the way you can spot that there's a quadratic order of complexity is when there's a nested loop. It's not always true that it's quadratic, but a lot of the times it is. And remember, it's a worst case scenario that we're looking at always, not an average case or a best case. It's the worst case scenario. So exponential is the last one, and exponential is like what we see when we do a recursive Fibonacci implementation. So I'm going to demonstrate this on the whiteboard because I think it makes it really clear. With exponential time, the time to execute doubles or more with each element in the input data set. Okay? So let me demonstrate this on the whiteboard because I think it helps to make it clear. You should really avoid exponential complexity. So that's one of the reasons that recursion is typically a bad idea, because there's always this danger of getting into exponential complexity depending on what your algorithm is doing, and you have to be really concerned about the size of your data set. So if you know the size of your data set's never going to get like extremely big, then it's okay to have exponential complexity. But if there's any risk of a really large data set, then you don't want to do this. This will like crash servers and stuff like that. So it's not good. And so this is what we saw. If you do a recursive, this implementation of Fibonacci, and you give it a number like 10,000, it's not going to work. Like I mean, if you have a supercomputer, it'll be fine, but yeah, it's not going to go well. Yeah, you remember that, don't you, Glenn? Yeah. Okay. So let me show you why. Let me show you what happens when we do Fibonacci recursive. Stop my recording because it's not going to be helpful.